Thank you. I'd like to thank everyone for coming in here. My nightmare was there would be 4 people in the room, and we have a fairly good group in here, so it's nice to see. So there is one other person at PSU that, well, formerly at PSU, that actually has used this microscope. That was my student worker, Brian. As students do, they move on. Last time I talked to him, he's a microscopist at Intel. We put a lot of students into Intel, into Lam Research, and other companies. Heck, we've got a lot of really talented people that come through the CEMN as part of their education from all of you, whether that be geology, mechanical engineering, chemistry, physics. It's some pretty talented people here at the university. And so what is all this gobbledygook? Well, Helios is the specific line of microscope. It's a dual beam. DB is a dual beam, and ours happens to be a plasma fib. Not all fibs are plasma fib. G4 is generation 4. Prior to this, Thermo Fisher Scientific, they used numbers that were kind of descriptive. You had a 400, which had like a 4-inch size chamber, and a 600 series, which had a 6-inch chamber, and this whole list of options. And so the UXE kind of roughly describes what options are on this particular microscope. I think that the U is monochromated. I'm not 100% sure of that, and don't ask me what the XE is. It's not, I don't believe it's xenon, because I'm pretty sure I've seen XE on gallium microscopes as well. So sometimes we retire microscopes. That picture got about 230 something thousand views on LinkedIn. That's our old Syrian SEM. That was the second microscope of the lab. And for those who are wondering, yes, I did get my shirt back. It is not a Hawaiian shirt. It's actually a Bula shirt. It's been to Fiji a few times. I love that machine. I spent over 3,000 hours on that microscope. It was a great microscope. It was a single beam, but it was pretty limited. It was not a good microscope for geologists like we have in this room, because there was no backscatter detector in it. But it was a great microscope for people who wanted to do high resolution imaging. And sometimes we get a new microscope. And to be honest, the center's had new microscopes, but we've never had a new dual beam. Our first dual beam that was here when I started back in 2009, that was a certified refurbished FEI DB-237. You could put a 25 millimeter diameter sample in it. The geologists pretty much hated it. The metallurgists pretty much hated it because it was very semiconductor centric, and you would have to really cut your samples down to make them fit. Our second dual beam fib was actually a donation with a Helios 400S. I loved that microscope, but there was a reason it was donated. It took about $500,000 to really get everything sorted out. We had to put a stage in it. We had to put a lens in it, all new consumables, some vacuum pumps. It was a lot of work, but it was a great microscope. We used it for a long time. It, however, was very unfortunately limited, and that we didn't have any spectroscopy on it. And so then we had the opportunity to get this microscope. This microscope, it came out of Hillsboro, out of Thermo Fisher's Nanoport. It's a certified refurbished machine. There were actually 2 26-foot moving vans that brought it in, and it almost didn't make it off the moving vans because the moving company decided to back 2 trucks up together and try to lower the lift gates down together. This thing almost tumbled off. It's $1 million microscope in the used market. It was pretty crazy. And sometimes we have to move a microscope. As our PSU folks all know, we had to do a building remodel of Science Building 1. It's in the process of becoming Bernier Science Center. Given the ventilation, I mean, by that I mean no windows or walls, it was not really an option to not move microscopes out. So we packaged this thing back up, and it sat in a box for the better part of a year while we're doing remodeling. And when we brought it back, we had to be careful not to interfere with the streetcar. That would have been a multi-million-dollar accident. And you can see a couple of riggers standing there discussing how they're going to do things. There's a reason I believe in hiring riggers, hire professionals. It's called third-party liability. They have extra insurance. So some of the things we expect from a microscope are pictures. Anyone have any thoughts on what this picture might be?
Money.
Yeah, John, you're right. It's money. What kind of money? Oh, no. You got it wrong. That would cost too much money. It's 4 cents less than that. This is a penny. This is Abe Lincoln. Yeah. This picture was actually done on the microscope you retired, but I love it. I break it out from time to time. This was done by Alpha von Nadaraja. He was a Rolf Koenenkamp student in physics. And he was working on deposition of zinc oxide nanorods. So it's a great way to demonstrate that when you magnify in, there can be more information there. I really like zinc oxide because it's a hexagonal structure and it costs, a couple of pennies to actually do a deposition like this. So now really what we're here for is to answer what is a dual beam fib and what can this microscope do? Now you can actually read the press release that's referenced on this image. Sean did a nice little press release. It'll take you all of 2 minutes, but at least those of you who are here for credit, you're going to have to spend like 50 minutes listening to me drone on about microscopes, and hopefully you'll enjoy it and learn something about it. So we have all kinds of things in microscopy and on this microscope. There's maps and IFAST and slice and view and lift out, multi-chem precursor gas injection system, spectroscopy, spin milling, rocking milling, e-beam lithography, ion beam lithography. A lot of this is not even interesting to most of the people in this room. However, there's probably some people online where some of this will be interesting. We cannot talk about all of this. Generally an SEM class, we've got Rick Hugo out here in the audience, one of our geology professors. He teaches an SEM class. That's a one-term class. There's another one-term class for SEM. Generally, dual beam fib would be a second-term follow-up to that one-term class. So we're only going to kind of briefly touch on some of the stuff. So MAPS is a correlative workflow and montaging software that's built into the microscope. And I'll show you a very brief example of a not too interesting sample to give you an idea how that works. IFAST is a scripting language. So for those who are maybe going to be doing the same kind of thing over and over again, you can write scripts and do some automation work. Lift out is a way we actually take a chunk of material out of our bulk sample. It could be to do some other kind of analysis. Usually in our case at this university, it would be low voltage stem analysis, since we no longer have a TEM, or somebody is going to take the sample to one of the other universities that does have a TEM. The multi-chem precursor gas injection system, this is like one of the cool things to me. I've never dealt with one of these before this microscope. It's a couple $100,000 add-on before we've only had single gas. It allows us to do depositions to protect the surfaces of our sample, to weld chunks that we lift out onto something else. There's also etch rate enhancers in here. You can do depositions with electron beam, but it's 10 times slower roughly than ion beam. That has advantages for certain applications. We're not going to talk about that today, but anyone who does want to talk about that, please come find me. My whole point to this talk is to give you a general overview, and then I'm hoping there'll be a lot of questions. And if several people have the same question, well, guess what? That's another talk. Spectroscopy. This microscope does have energy dispersive X-ray spectroscopy and electron backscatter diffraction spectroscopy. However, sadly, we are still waiting for the manufacturer to come in and reinstall those spectrometers. They're not up and running. I'll show you a little bit of historical data. Spin milling is a technique that makes your very expensive microscope kind of act like a inexpensive broadbeam ion miller, but you can transition without having to expose your sample to atmosphere. And rocking milling is kind of a niche technique, but it's a way to actually speed up your milling process. And then I'll show you some lithography here. We're gonna see some pretty cool lithography. And I've done photolithography. I'm not like an expert in electron beam lithography or ion beam lithography. I've done a lot of that, but in my electronics days, I was a photolithography process engineer. So this is a view of kind of the standard user interface in quad mode. So the top left in this view is configured to be electron beam. And if you look at the data bar at the bottom, you'll see kind of a little atom there. The top right is our ion beam. The bottom left is the navigation camera. So when we put a sample in the chamber, we'll get like an optical picture. And when I can double click on places in that optical picture, it will drive the stage to that location. Makes it a lot easier to find stuff. We have ways we've done this before in other microscopes where we've taken flatbed scanners, scanned like geological thin sections. I've taken pictures off my cell phone, emailed them to myself, and like use that, find fiducial recognition. This is kind of more convenient. And then there's in The bottom right view, this is our nav camera. And the idea of that camera is not to run into the expensive bits in the microscope. This is the largest chamber dual beam and stage we've had. As I mentioned previously, the 237 was 25 millimeter. Our Helios 400, technically it could do a 75 millimeter sample, but only 6 millimeters tall. And we did not have the special sample holder for that. So really we were kind of stuck with 25 millimeter samples or something hanging over a little bit. This microscope is rated for 150 millimeters. I don't know if there's limitations with possibly some installed accessory items. We do run into that in microscopy. Sometimes your accessory items can interfere with some of your travel and your size. The picture to the right here is actually a 4-inch stub, and that's a copper gasket that came off of our Zeiss SEM in its most recent maintenance that I just kind of taped on there for a size reference and also to have something to cut on. So dual beam fib application. So really dual beam means that we have two beams. Primary beam is typically an electron beam. The secondary beam is an ion beam. More often than not, that second beam is gallium. Plasma is kind of coming into its own these days. But you know, there's other gases for plasma, the plasma side. There's other metals for the liquid ion metal side. I mean, people have used bismuth. On the picture on the right, I'm actually going to add some annotation here. Hopefully my animation works okay. So you can note the electron lens, and there's probably a 1 millimeter gap between that and the detector that's inserted below it. Ion lens, the backscatter detector. So this is something none of our other dual beam fibs have had in the past. The only thing we've had this in would be our Zeiss SEM. And this is one of many sample holders we have for the microscope. This is a front view. That camera's in the back of the microscope looking forward, and this is a little bit out of focus, and I would say I'm sorry about that, but the reason I took this picture is I was trying to look at the electron scintillator screen as we were putting this back together, see what kind of condition that was in. And I could get a good enough view from this to know it needed to be replaced. It had maybe 1,000 hours on that screen. It's a $2,000 part. And that's the actual chamber cam from the previous view. So it's important to understand how magnification is defined. Some people, you know, in here might be old enough to have worked with film on microscopes. And in the old days, film was usually Polaroid 545, which is a 4x5 inch, and so magnification was kind of a standard thing. People understood what it meant. In the days of digital microscopy, we kind of define magnification as the width of the image over the width of the scan. And so if you're seeing this on the big screen in the room, it's definitely much higher magnification than the monitor on my microscope. You know, maybe some people online are seeing this on a cell phone or an iPad or something like that. That'd probably be much less magnification than I had and when I actually saw this. And so the next thing people tend to talk about are scale bars, but the problem with scale bars on most microscopes is the scale bar will change with magnification and length before it jumps to the next size range. So in this case, where we have a 300 nanometer scale bar and a 500,000 magnification, there's a range of magnifications that would give me a 300 nanometer scale bar. And saying a 300 nanometer scale bar, just that doesn't really mean a whole lot to me sometimes. Horizontal field width is a great one. You'll see that on the kind of in the middle of the data bar on the bottom. Horizontal field width tells us the width. In this case, it's it's about let's call that 7/8 of a micron. It's a little bit less than that. That's getting there pretty good. So this is kind of a pretty good sample. This is a secondary electron image in immersion mode. So it's the TLD is the through lens detector. That does work in immersion mode or non-immersion mode. Immersion mode is nowadays called mode 2. We cannot use that mode with ferromagnetic samples as the lens becomes a very high power magnet, and it will tend to suck your sample into the lens, destroying it. And that has happened in this lab, not on this microscope, on another microscope, but that has happened. And it's very expensive. It makes me sad when it happens. Now I just changed the magnification. This is the same image we just saw, only bigger since it's single field of view. This is, I'm guessing at least Rick knows what this is. What do you think, Rick? No? Anyone else? I thought Rick would get this one in a heartbeat. Anyone else got any thoughts of what this sample is? I'm sorry? Christmas ornaments. There you go. You're not too far off. Only they're nanoscale. This is actually what is considered to be a low to medium resolution bulk electron microscopy standard. It is 10 balls on graphitic carbon. And if you look around, you can find some areas where there'll be some smaller balls like this because most of them are much, much bigger. And I just had, we do some amount of work with some local businesses as well who help support the lab. And I just had a company come in and they were trying to get some micrographs, and that kind of brought me to think about I should probably talk a little bit about resolution because they had this desktop SEM and they're like, we should be able to see this layer, and we simply can't see this layer. And when I explained resolution and how I like to say as bulk microscopists, we kind of lie about it a little bit. It started to make a little sense to the customer. So generally in optics, the Rayleigh criterion is used. You can see the equation here. Theta is actually sine theta. And we get these airy discs pictured to the right. This is a top view of an airy disc. I kind of like the cross-sectional view, but I didn't want to make my own drawing since I'm not a very good artist. So the bright spot indicates where the main diffraction information is. In the top view, we would call that well separated. We can resolve that. In the middle view, we would say that's somewhat separated. That still would be considered resolvable, although we might not be able to get a whole lot of information out of it because we have overlapping. And on the bottom one, that's not resolved, or it's some kind of optical aberration that's happened there. So the Rayleigh criterion, if you consider your area disk to be a Gaussian distribution, you would have to have 20% separation between the peaks before people will in general say that this is two things. It does not tell you what two things they are. It just says there are two things here. The SEM and FIB microscopy definitions, like I say, I think we lie a little bit here because we use edge contrast methodology, which means there's a test specimen like I showed you previously, although we would use gold carbon for this microscope because it's extreme high resolution. And we look for a change in contrast from 65% to 35%. Rayleigh criterion would imply that we have to go from 90% to 10%. And so our 0.5 nanometer resolution might mean we can see particles maybe 3 or 4 nanometers in size.
What are the symbols in that formula? You said sine theta, but then
It's sine theta is approximately equal to 1.22 wavelength of light times the diameter of the aperture. So I think for me, I'm a little bit lazy. I just kind of the lazy backwoods way to do this, since I grew up in rural areas, half the wavelength of light. That's pretty close. It works out pretty well in most cases to give you an idea. And if you're an optics person, you can do the calculations. I'm not an optics person. So I'm not quite sure this is going to work out for me. I was going to show you some examples of some micrographs here, and I'm not sure that's going to pop up on the screen. Yeah, okay, next. That's going to pop up on the screen. So periodically you'll see some image contests, whether they be SEM, TEM, whatever, general microscopy stuff. This nice little flower looking image here. That's actually like a vanadium oxide nanostructure that's been false colored. So I just happened to stumble onto this over the weekend, and I thought, wow, I've got to kind of show that. It's pretty cool. So this was Yongjin Beek. She did her master's in material science engineering here at PSU. She's a PhD candidate at Auburn now, and used to come into the lab. So I know her. She used to come into the lab and do some work. We used to do some EBSD work together. And I thought that was pretty cool. But in SEM, there's no colors. It's only grayscale. So people do false coloring for artistic reasons or to convey other information. And I thought, well, that's cool. Let's show somebody who was successful from this university. And there's other kinds of images here just to give some general ideas, like biological image here. some bugs. Bugs can be my favorite stuff. I really like bugs when I'm doing education outreach with kids. Heck, I've done bugs for OHSU. We did some fruit fly work at one point. Oh boy. And now we gotta, let's see here. It should be easy. Okay, we were there. But hopefully that was a little bit interesting to you. Well, something that becomes really important in EM is detector configuration and orientations. We have some detectors are top looking, some detectors are side looking. We get shadow. I picked the backscatter detector for 3 of these 4 images in here because backscatter detectors are the most interesting thing to geologists. And this lecture is primarily geologists. If you notice on the data bar, the top left image, it says CBS, which is concentric backscatter detector. That's purely top. The image in the top right, that's ABS, annular backscatter detector. It's the same detector. It's just a software configuration change and an amplifier change. You can see like a little bit of shadow in the ABS from, say, around 2 o'clock down to the 5 o'clock position on some of these tin balls. And that was simply the reason I turned off one of the segments. So I could create shadow, I could better understand the 3D morphology that's present. On the bottom left image, I actually inverted that segment, and that's why it's like really black kind of in there to show you a lot of contrast change from the edge. So we can see these are very spheroidal. They're very much like 3D in nature, although we don't really have an idea of like how deep they are. And then the bottom right detector is a completely different detector. This detector is in chamber, but it's kind of high angle in chamber. It's the it's a secondary ion and electron detector. I forget what the ICE acronym stands for. I think it's ion conversion and electron detector. And in this case, we kind of get some highlighting on this particular sample because if you look at least the larger spheres in here, you can see it's very much whiter around the perimeter. And I think that has kind of a nice effect. So I'm going to talk very briefly about maps. As I mentioned earlier, that's our correlative software. So I took a stub. Hopefully you guys can see my mouse cursor over it. I decided I wanted to examine this specimen on this particular calibration standard. Guess what? You've already seen some of the pictures of it. So I went and did a 2.6 gigapixel image. Yes, that's gigas, 2.6 billion pixels. It's about a 7 millimeter diameter circle. I could do more. This just becomes limited on computer memory, computer data storage. I mean, we could actually probably use a big data center if we really want to get into big data. We have the hardware to do a lot of big data stuff. And I kind of took a image here and I binned the crud out of it because there's no way in heck it was ever going to open on this computer, maybe in an hour, and we'd be done. So this is kind of a little overview. This was I believe this was 4 frames that were stitched together on this particular sample. It stitched really nicely. Not all samples stitched this well. And because I used a backscatter detector that's top mounted, we have very even lighting. We refer to our electrons as lighting. I have no idea why. I'm not old enough for that, but and here's an example of maybe the wrong way to do this. I did a subset out of the original data with an Everhart Thornley detector, and we can definitely see some like vertical striping, and the vertical striping is not from alignment, it's from shadow due to the angle of the electron detector. And that shadow will change. The more of these frames you do, the more change you'll get. It can become very objectionable. There may be software ways that I could correct that. I've not really looked into that. And another way we can get images, low voltage stem. Since we don't have a TM anymore, if you're a particle person like Andrea Goforth, our director in here, this is kind of how she's going to be getting some data, I think. And Ken Stedman down in biology as well. We have the special holder that goes in, a stem detector that goes underneath here. This is I think this is gold. I'm not 100% sure if this is gold. This is actually a standard for STEM to do resolution checks on the microscope. This image came out of our old lab, and it was just about 6 angstrom resolution, roughly. This image as well came out of our old lab. This nice flower here is actually Ken Steadman's virus particles at 1.2 million. Oh, funny, Eric, I see Eric Dunkel on here. I know that guy. Just popped up a comment. Good to see you on here, Eric. And then for some spectroscopy, and I threw some things in spectroscopy that aren't really spectroscopy. Because they happen off the spectroscopy computer. But we're going to start with spectroscopy. So this is actually some work that I work on. So this is actually a solder ball on a circuit board connecting a computer chip package to the circuit board. We have all of these things we call interconnects. That's the type of things I work on. I'm not so much a semiconductor person as an electronics person. I do some amount of semiconductor work in failure analysis world. But this is actually a tin bismuth here. And we can get a spectrum. Many of you might have seen an EDS spectra. This is a sum spectra, everything that was collected in here. And the green represents tin, this kind of, I'm going to call it purplish color because I had the small box of crayons growing up. I don't know all of the colors. That's going to be our bismuth layer. This bismuth up there, this really nice purple up here, that's actually a nickel layer, which is common to keep your copper from oxidizing and also improve bonding. And then the kind of orangish color is copper. I picked that. It looks kind of like an oxidized copper, but this is far from oxidized. And we can also do some electron backscatter diffraction. I throw that in, like I say, with the spectroscopy, even though it's not really spectroscopy because it happens on the same computer and we're usually doing spectroscopy at the same time. It's actually a crystallographic imaging technique. It gives us information about the type of crystal and how it's oriented. In this case, we only looked at the tin because the bismuth didn't matter to the information we were trying to find. And as some of our geology types in here will probably tell you, you can put an awful lot of different crystals in. When you do that, you sometimes get misassignments. No matter what, the more crystals you have, pretty much it slows down the acquisition speed. And I was trying to get this done in about 6 or 8 minutes on the scan. And so this is an older IPF on the left side. So it's actually a metallurgy sample. It's additive manufactured titanium 6-4. And it's, I'm going to call it kind of a mess. You can see there's you can see my mouse cursor. You can see there's like this black scratch here. That's actually a scratch in the material from the polishing. We did not do hydrofluoric. Normally you would do like a little bit of hydrofluoric for polishing this, but not in our lab, not on a spinning wheel, no. And the image to the right is actually a Kikuchi pattern. And so that's Kikuchi diffraction was, it's named after this Japanese guy named Kikuchi who came up with this in TEM. And the advent of like high-speed computing and fast cameras and being able to digitize things got it into SEM. So now we can do diffraction over very large areas. I know Alex Ruzicka, he does like centimeter scale montages, several centimeter scale montages. So you can gain a lot of statistics when you're inside TEM. You can't really get a lot of statistics out of that because your specimen is typically maybe 6 to 10 square microns. And I see a lot of people looking at this kind of funny. One thing to note is that the key on the left is what really applies here because this is 99% cubic and roughly 1% hexagonal, which would be the key on the right. This is actually a montage done through our spectroscopy software. So we have this old standards block floating around that doesn't have proper documentation to it, which means it's not really a standards block anymore. But the things that are pure and that don't oxidize, they come up pretty much what you would expect them to. So I set up a whole bunch of frames of view, and you can see there's a lot of misstitching here, especially out in the brass block area, because there's not enough information at the resolution I used to get like good alignments. But the actual specimens themselves are pretty good. And I decided to pick one right here that I highlighted. Because I knew there were some mineral things in that area, although it's not all minerals. Most of these are pures and other compounds. And I did luck out. I did find the right one. That was, or one of the right ones anyway. So we ended up with this spectra here. So this is a calcium phosphate with a little bit of fluorine in it. And I was like, yeehaw, apatite. I learned something about geology, and well, according to what information I have, I think I got that right, but I'm sure our geologists in the room can tell me. And then this is our weight quantification. I did not try to adjust this for oxide percentage. This is just raw weights. Things that are low on the periodic table, they tend to overestimate given the algorithms, especially on samples that are coded. So sometimes we have to put some adjustments in. Now into my favorite beam, the ion beam. So this chart, this is Noel Smith. He was at FEI at the time. Now he's Oregon Physics. And the things we really want to look at here are the white line and the solid black line. The white line is resolution of a gallium fib. Keep in mind, this paper was done in 2006, so it's nearly 18 years old now. And the black line would be a inductively coupled plasma fib. And we can see very low probe currents, there's a big advantage to gallium. So if you want to do lithography or make your life a lot easier for doing TM sample preparation, a gallium machine is really nice to have. But once you get up in this view to around 50 nanoamps or thereabouts, the plasma becomes advantageous, where you have a much smaller beam size. And I find 60 nanoamps and 200 nanoamps on our microscope to be very good. Most dual beam gallium fibs cap out at between 20 and 100 nanoamps somewhere, depending on the model. And this is a little bit newer chart. Now we're down into gallium losing its advantage in about 35 nanoamps. This was Basim, and I know Lucille Giannuzzi. She used to be at Thermo Fisher. She actually came into our lab one time and did a little bit of work with Tony Chen, the old manager. And this is still old data. This is 2014, but this is maybe a little bit closer to what we should kind of expect from our microscope. Our microscope was actually manufactured in 2017. We dropped the PO in 2019. It showed up in February 2020. And we got it partway assembled and we're told to go home, and didn't come back for 6 weeks due to COVID. Unfortunately, we had a customer who was working on some ventilator parts that needed some qualification work done before they could go into service, and that got us back in the lab. So here's another view of our gasket. You can see there's a hole when we're tilted to 52 degrees. We're now normal to the ion beam. There's probably around 200 microns of spacing between the sample and the very expensive electron lens. So we really have to make sure that we are on top of it setting eucentric height. So eucentric is a point about which you can tilt and you do not have image translation. I will probably hate myself for saying, take out your phones, people, if you have them, and look at a spot. And when you can find a spot where you can tilt and not have a translation, that's eucentric. Now we have normal, which is where each beam would be looking to it. The ion beam's 52 degrees. So now we're looking at that normally. And of course, our SEM beam is like looking down this triangular edge. We're on the hypotenuse of the triangle. So that poses some problems you'll get to see later on, which are kind of fun to deal with. I mentioned gas precursor. So I decided I wanted to make a cut in this copper gasket because it's something there's no IP on. We can see here, if you can see my mouse cursor, there is a protective cap I put down. This is something we couldn't previously do, because this is actually a mixed protective cap. This is platinum carbon mix, which is a little bit harder. So it holds up to the beam a little bit better. And one of the things I try to teach people is be efficient in your deposition. The cost of a deposition is how long the valve is open for that precursor gas. Some of these gases can be hundreds of dollars an hour. DX gas, which is a rate enhancer, that's like $200 an hour to use that. Platinum is, I think, $3 a minute roughly when we did our refill last time. So there are certain current steps we have available. It's okay to make your deposition bigger so you can have a more efficient deposition. And in this case too, if I kind of blew through it on this one, I still had another place I could go next to it since it's not site specific. So this is a top view. This is ion view. And we can do imaging with the ion beam. It is destructive. You can get almost all of the same signals out of an ion beam as you can an electron beam, but you cannot get secondary electrons because secondary electrons are primary electrons from your electron column that have interacted elastically with an atom. So this would be a secondary. This is actually the way this detector is configured. It is configured instead of being an ion image, it's a secondary electron image using the ion beam as the generation source. So our sputtering is taking, as we're taking materials off, we're generating secondary electrons, which are defined in the physics world as having voltages of 50 electron volts and less. And then we can see here where I did like a little bit of polish to make it better. This prior image, I didn't quite get clear to my protective cap. That was intentional. I like to leave a little bit of space when I'm doing a high current mill. That's a 100 micron wide mill. I did that one at, I think this was 200 nanoamps, if I remember correctly. And then I did like a little 15 nanoamp polish there. And eventually I did like a lower current polish, and I come up with this nice little void. It's like, hoo-hoo, there's a defect in that copper. Not surprising. But we can see what we're seeing here in the various colorations. Well, one is curtaining. I did not do a great job polishing this for this demonstration. So that's your vertical striations that can be polished out, and we could make that better for sure. And we can see some grain refinement at the surface, and that's not too surprising because this has been squished between two vacuum components in order to form a seal. And here's like a little bit of a close-up. So if we wanted to turn this into a TEM lamella, this is a different sample. We would simply cut a pocket on the backside, attach a manipulator, lift it out, and weld it to a TEM grid. And here we can see this is a metal sample. I'm not sure what metal it is. I think this was steel, if I remember right. And that's pre-thinned. It's not clear to the thickness that we would need for doing STEM on it or transmission EBSD. But I didn't want to like go all the way there. This is from an old demo that we'd done. So speaking of transmission EBSD, one thing I haven't mentioned is the resolution differences. So EBSD in bulk, pretty much anyone these days will accept spatial resolution of 50 nanometers. The vast majority of people will accept 25 nanometers. Some people claim that you can get more information with even finer pitches. In transmission mode, you can certainly go below 10 nanometer according to publications. So it doesn't get you down to that TEM level, but it gets you an awful lot of the way there. Sorry, wrong way. So now we're seeing, this is going to be, especially if you're here in the room where we have the big screen, this is the biggest the Portland State University CEMN logo has ever been displayed. I haven't done a talk since before we had an official university logo. In fact, normally it's even much smaller on my screen. But I thought it'd be kind of fun to play around a little bit with lithography. And so I chose ion beam lithography because I don't have to break out the spin coater, and I didn't move my resist from the old lab. It was expired, so I just had it hazmat disposed of. So I wasn't going to do some electron beam lithography for that. But we can do that. So one of the problems that you're going to run into with something like this is that the colors are not uniform. And when I zoom in really tight and do a window snip, because if you actually like zoom in, cut, crop, and insert this, then PowerPoint wants to smooth it out for you, and you just end up with something blurry where you can't see the issue. Shows that we have a lot of grays in there. The microscope will interpret whatever you're telling it to do as do more of it where it's white and do none of it where it's black. And if it's some kind of gray in between, do something in proportion to the gray signal. With bitmaps, we can import bitmaps directly so long as they are 24-bit bitmaps. This was 32-bit. It turned out it was kind of a pain because Windows didn't want to let me convert it, even though I told it to save it as a 12-bit. I had to JPEG it and then go back into a 24-bit bitmap. That may have actually increased some of the defects in here. And here we can see a much smaller version, if you were on the microscope, of the CEMM logo. I did that as a 200 micron wide mill. It's about 48 microns high. And this is just a silicon substrate. Silicon is ideal if you get single crystal for these types of things because it will mill very uniformly being single crystal. It's the cheater's method, and I will cheat when I need to for something like this. If you notice, if you look at the actual PSU logo itself, you can see it looks kind of rounded. I think it has a neat artistic effect. And a lot of that rounding comes from all of those weird grayscales that are thrown in, and also the fact that the beam was a little bit fat for this application. I did this at 15 nanoamp, so I had a pretty fat beam, and plasma fib beam distribution is somewhat Gaussian. So you're going to be doing some milling with the tails, which is going to make matters a little bit worse. And the higher your current, the more tail you kind of have out that's hanging out there. But I was pretty happy with it. I liked it. I knew that there was going to be some defects. We can see on the left of the S how that's not fully developed, and at the top of the P that's not fully developed. And when we go back, that's because it's at the edge of the logo. I could fix that by modifying the logo, putting some white in. And so I did a little cross section here so you could actually see the rounding. Poor PSU logo. The actual logo itself is about 30 microns in this view. And then I did a quick organometallic deposition, which kind of turned into a nightmare using the inverse of our logo, which is white. And here in the electron beam view, you can see the gas injection needle and a teeny tiny little PSU logo out there. I didn't like the way it was developing because the C and center had some defects in it, so I changed my scanning technique. And I didn't move, I just redeposited on top of that. So now it kind of got a little ugly, but I thought, well, you know, I have an ion milling machine here. We can make this better. And so I started ion milling, and eventually we pretty quickly took off some of the protective cap. This was tungsten. I went cheap on this one. This was tungsten over our silicon, and we can see a little bit more developed where our PSU is looking pretty nice, but most of the tungsten's gone off the text. And almost completely gone, and kind of this is where at the point I stopped at. And I gave us a nice view, and this is an electron image of the PSU logo. Anyone have thoughts on what's wrong with this? Does it look funny?
Squash.
Yeah, it's a little squash because it's a 52-degree angle, and I didn't have the scan compensation set correctly for this particular imaging mode. I reset it, and then it came out a little bit square, more like it should be. That's more how it should be. This is the smallest PSU logo as far as I'm aware. It's about 1/3 the diameter of a human hair. I did kind of luck out and get it at 30 microns. That wasn't like an intentional choice, but I wanted this to be big enough to where I could break my own record later on. And there's some things I don't like about plasma fib. We have like stupid high currents sometimes. We get 2.5 microamps of ion beam current. It generates massive amounts of electron signal. This is the flue screen that I was taking a picture of earlier where I showed the front chamber view that came out, and you can see how it's very damaged and discolored. That's a couple $1,000 part. It had maybe 1,000 hours on it. And the ion column is kind of hard on ion pumps. So far, that's my collection of ion pumps, and you have to keep in mind this was in storage for more than a year. I went personally a year and a half without actually using this microscope. So I'm kind of trying to relearn things myself, but I'm sure we'll add to that. We'll add at least one more pump this year. So there's some reliability issues you can get to on these. And I'm good for questions. I hope you enjoyed it.